Hello, in this video I'd like to talk about the integrated rate law. In the previous section, we learned about the differential rate law, which is a mathematical equation that shows how the rate of reaction varies as a function of concentration. So, for the hypothetical reaction, A forms products, we can write the rate law as follows. The rate is equal to the decrease in concentration of A with respect to time, and that is equal to the rate constant K times the concentration A raised to the power of n, where n is the kinetic order, 0, 1, or 2. Using a mathematical technique called integration, we can convert the differential rate law to obtain the integrated rate law. And the integrated rate law is a mathematical equation that shows how the concentration varies as a function of time. And for each of the three kinetic orders we considered, there is a specific form of the integrated rate law. And once you have one, you can simply write the other. So the question is, what do they look like? Well, let's look and see. So, for a zero-order reaction, if A forming products is zero order in A, the differential rate law looks like that. And when we integrate that, we obtain the integrated rate law, which is as follows. The concentration of A equals negative rate constant times time plus the initial concentration of A. A is the remaining concentration at time t. K is the rate constant in moles per liter per second. T is the time elapsed, and A naught is the initial concentration of A. Okay? So for a zero-order reaction, the rate of the reaction is constant, which we knew. We simply multiply the rate constant by the time elapsed, subtract that from the initial concentration, and that gives us the remaining concentration. So what would a graph of concentration versus time look like? Well, clearly the integrated rate law is of the form y equals mx plus b with a negative slope. So if I were to graph concentration as a function of time, I would obtain a straight line with a negative slope. Okay? So, if a graph of concentration versus time gives you a straight line, then you know the reaction is zero order with respect to A, and you can simply write both the integrated rate law and the differential rate law. How convenient is that? And the K, the rate constant, is simply the negative of the slope of the line. Now, for a first order reaction, if A forming products is first order with respect to A, we know the differential rate law looks like this. Integrating that to get the integrated rate law gives us the following. The concentration of A equals the initial concentration of A times E raised to the power of negative K times T. Or, if I take the natural logarithm of both sides, I obtain the logarithmic form of the integrated rate law for a first order reaction. The natural logarithm of A equals negative KT plus the natural logarithm of the original concentration of A. Again, these are as before. Now the rate constant is in reciprocal seconds. The rate is dependent on concentration. The concentration of A decays exponentially with time. In the natural logarithm form, the equation has the form y equals mx plus b. And if that's not clear, I'll label it y equals mx plus b. So the question is, what would a graph of natural logarithm of concentration versus time look like? Well, if I were to graph natural logarithm versus time for a first order reaction, I would see a straight line with a negative slope. So, if a graph of natural logarithm of concentration versus time gives a straight line, then you know the reaction is first order with respect to A, and all you simply have to do is write both the differential and integrated rate laws. And K is the negative of the slope of the line. For a second order reaction, if it is second order in A, the differential rate law looks like that. The integrated rate law looks like this. The reciprocal of the concentration of A is equal to positive KT plus 1 over the concentration of the initial concentration of A. Again, these quantities are the same. Now, the unit on the rate constant is in liters per mole per second. The rate is dependent upon concentration. The equation has the form y equals mx plus b, and I'll label that if that's not clear. Y equals mx plus b. So the question is, what would a graph of reciprocal of concentration versus time look like? Well, here, graphing that would give us a straight line now with a positive slope. So if graphing reciprocal of concentration versus time gives a straight line, then you know the reaction is second order with respect to the concentration of A, and you can simply write both the integrated rate law and the differential rate law. Now, K is the slope of the line. So, what can we do with all of this? You can determine the kinetic order of the reaction graphically, and then once you've determined the order, 0 first or second, then you can simply write the corresponding differential and integrated rate laws. So, here's how the graphical method works. If I get a straight line when I plot concentration versus time, then the reaction is zero order. The slope of the line is negative K. There's the differential rate law and the integrated rate law. I can simply write them. On the other hand, if I get a straight line when I plot the natural logarithm of the concentration of A versus time, then I conclude it's first order, the slope is negative K, and I can simply write both the differential and integrated rate laws. Finally, if I get a straight line when I graph reciprocal of concentration of A versus time, then the reaction is second order, the slope of the line is K, and I can write both the integrated and differential rate laws. How convenient is that? So let's take an example of this. Okay, let's talk about this. Using the integrated rate law, you can calculate the remaining concentration of reactant at a specified time, calculate the time required for the initial concentration to decrease to either a specified value or to a percentage of the reaction completion, calculate the half-life of the reaction, assuming you know the initial concentration in K, which we'll get to in the next video, or calculate K given values of concentration, initial concentration, and time. So here's an example. The decomposition of hydrogen peroxide was studied, and the following data were obtained at a particular temperature. So starting with 1 molar hydrogen peroxide, we allow 3,600 seconds to elapse, and we measure the concentration at time intervals. So assuming that we define the rate as the decrease in concentration of hydrogen peroxide with respect to time, determine the rate law, the integrated rate law, and the value of K. Then, having done that, calculate the remaining concentration of hydrogen peroxide after 4,000 seconds. Now, this sounds like a lot of repetitive calculations, so here's where you're going to need to use Microsoft Excel or some other spreadsheet program to perform your calculations and to do your graphing. And I'll show you what that looks like. So, here you can see I simply took the raw data, concentration as a function of time, and I graphed concentration versus time. Does that look like a straight line to you? Sure doesn't to me. What do we conclude from the fact that a graph of concentration versus time does not give a straight line? We can conclude that it is not zero order. Because if it were zero order with respect to hydrogen peroxide, we would have a straight line with a negative slope. So let's try another. Here I'm graphing the reciprocal of the concentration of hydrogen peroxide versus time. Does that look like a straight line with positive slope? Sure doesn't to me. So again, we conclude that it is not second order with respect to hydrogen peroxide. I think you see where this is heading, don't you? Finally, I calculate and graph the the natural logarithm of the concentration of hydrogen peroxide versus time. What do you know? I get a straight line with a negative slope. So that lets me conclude that the reaction is first order with respect to the concentration of hydrogen peroxide. I can now simply write the integrated rate law and the differential rate law, and furthermore, I can simply use the slope, or I should say the negative slope of the line, because that is the value of K, the first order rate constant for this reaction. So let's finish the problem. Okay? So I can now simply write the rate law. Decrease in concentration of hydrogen peroxide with respect to time is equal to K times the concentration of hydrogen peroxide, where K is equal to, let me check that number again, 8.35 times 10 to the negative fourth. And because time was measured in seconds, I know that the unit on K is going to be reciprocal seconds. I can write the rate law, the integrated rate law. Concentration of hydrogen peroxide is the initial concentration of hydrogen peroxide times e to the negative kt. And now I can solve the problem. I can calculate the remaining concentration of hydrogen peroxide after 4,000 seconds simply by plugging into the integrated rate law. So this is equal to 1.00 mole per liter times e raised to the power of negative 8.35 times 10 to the negative fourth reciprocal seconds times the time, 4,000 seconds, Notice that seconds cancel and the exponent is unitless as it needs to be. And when I perform the calculation, I obtain my final value. Concentration of hydrogen peroxide after 4,000 seconds is 0.0354 moles per liter, which, if you look back at the data table, is consistent because it's less than the lower value we've seen. Okay, in the next video, I will do several more examples of using integrated rate laws to calculate times and concentrations, and we'll also talk about the concept of half-life. See you then.